All right, welcome to chapter 18. This is electrical energy and capacitance. This chapter is not very long, so let's see what we can get to. Electrical potential energy. This is the potential energy associated with an object due to its position relative to a source of electric force. Remember before we had talked about elastic potential energy, which was due to the stretched properties of it, and we talked about gravitational potential energy. We're bringing a different type of potential energy in, which is the electrical potential energy. It's due to the position to a source of electric force. Electric potential energy is the form of mechanical work. Remember we talked about mechanical work, the sum of all energies. Electric potential energy can be associated with a charge in a uniform field. We can find that electric potential energy in a uniform field with this next formula I'm going to show you. You really don't have to write down the formulas in these notes right here because I'm going to go over them again when we do the problems. You can write them down now if you want, but you can wait until we get to the problems if you want. Basically, the electric potential energy is equal to negative Q. Q is the charge, capital E is electric field, and D is the distance from the field. As you read up there, the displacement from the reference point in the direction of the field. This seems kind of complicated, but they're actually pretty easy. Remember, energy, all energies are in joules, Q is in coulombs, E, electric field is in Newton per coulomb, and the distance is in meters. SI unit for energy is joules, we have coulombs, newtons per coulomb, and distance is meters, just what I just said. I'm brilliant. Next, electric potential energy can be associated with a pair of charges. So two charges together. It can be found almost identical to the formula that we talked about in the last chapter, in chapter 17, where we did the electric force equation. This one's almost the same way. You see that the electric potential energy is Kc, our constant that we had before, Q1, Q2 divided by R. But the only difference here is that R is not squared. So this way it's going to give you joules and not newtons. What I just said, electric potential, this is going to be something we come back to over and over again. This is the electric potential energy associated with a charged particle divided by the charge of the particle. And this potential difference is the main one, the real one that we're going to work with in chapters 19 and 20 over and over again. This is basically your voltage. Potential difference is voltage. It's the same as electric potential with a little bit different. It's the change in electric potential, where the first one, where electric potential is just the electric potential associated with, this is the change in electric potential energy associated with a charged particle, divided by the charge of the particle. So this would have the triangle in front of it. We can find the change in potential energy with this formula. The V is your potential difference, equals the electric potential energy divided by the charge. And most of the time we're going to be talking about electrons and protons, but sometimes we're going to take different types of charges. SI unit for potential difference is the volt. That's your voltage. We have another formula that the potential difference is equal to negative times the electric field times distance. One more, potential difference equals our K constant times our charge divided by the distance. Again, I wouldn't worry about writing all the formulas down right here. Wait until we do the problems, because we're not going to do all of these formulas. We're not going to work with all of them. Alright, capacitance. A capacitance is the ratio of charge to potential difference. A capacitor, you heard of the flux capacitor from Back to the Future? 1.21 gigawatts. Come on, all of you Back to the Future fans. A capacitor has the ability of a conductor to store energy in the form of electrically separated charges. So as the electricity is flowing through it, it's separating charges out and storing them for later use. We can find capacitance with this formula. C equals Q. The capital Q is still the same as charge, but it's the charge of a plate. It's a larger charge, not a point charge like our little q was, divided by the potential difference, our volts. The SI unit for capacitance is the farad. It's capital F. Farad, capital F. Q is the charge, much like the little q we worked with before. Capacitance depends on the size and shape of the capacitor. There are all different sizes and shapes of capacitors to hold a little bit of charge, to hold a lot of charge. And we might see some pictures of some later on. This is the one we're actually going to be using. I know we're going to do problems with this, that the electric potential energy is equal to 1/2 times the capacitance times the potential difference squared. And I believe that's all the notes. Like I said, these are very short. We're going to do more problems with these. So we'll see you in the workbook.